Alrighty, this week we're going to start a discussion on limiting and excess reactants. It really builds on the mole-to-mole conversion factors that we talked about last week. Usually I start this lecture with an analogy involving cupcakes. However, since your lab this week uses very similar cooking analogies, I'm just going to encourage you all to start looking at that lab, doing that lab, working with the simulation. It's intended to be complementary, so you don't have to be an expert on limiting excess reactants in order to successfully complete the lab. You'll learn a lot about this material by doing the lab, and then hopefully all the pieces will come together for you. So the first thing is this idea of a limiting reactant. And I'm going to use the abbreviation LR for limiting reactant when we go through our problems. So that's the reactant that runs out first. You're going to have, when we do our calculation, you're going to have 0 grams or 0 moles left over. Finally, how do we identify a limiting reactant? We want to find the thing that produces the least amount of product. So our ingredient that produces the least amount of product is going to be our limiting reactant. Let's see that in play. So we have a balanced equation, and I filled in the quantities. So say you are a chemist and you go to the stock room and you're like, okay, I have 3 moles of sodium available and I have 3 moles of diatomic bromine available. And then the question becomes, how much sodium bromide can I produce with the ingredients, the reactants that I have on hand? These types of problems, limiting and excess reactant problems, always involve 2 setups minimum. So 2 separate lines. We're going to analyze each reactant individually. So let's pretend that the information about the bromine isn't even here. So all you know is that you have 3 moles of sodium. And then I ask you how much sodium bromide can be produced. Well, that should ring a bell. You did a lot of problems like that last week. So we're going to start with the 3 moles of sodium. And you want to get rid of moles of sodium. So you put that in the denominator. And we're interested in how much of this product we can make from our 3 moles of sodium. So I'm going to put moles of sodium bromide in the numerator. Remember, at this point, because it's a mole-to-mole conversion factor, I need to grab those coefficients. So I have a 2 in front of my sodium and a 2 in front of my sodium bromide. Moles of sodium, cancel with moles of sodium, and I'm left with moles of sodium bromide. So if I had 3 moles of sodium, and again, I just made up that number for this problem, then I would be able to produce 3 moles of sodium bromide. Okay, so that's step 1. Step 2 is going to look super similar, except now we're going to ignore the sodium. And the question we need to ask ourselves is, how much sodium bromide can we produce from just the 3 moles of diatomic bromine? Start with what they gave us. Think about what we're trying to get rid of. We're interested in that. Grab those mole-to-mole conversion factors. So we have a 1 out front here that's understood. And a 2 in front of the sodium bromide. Units canceling. And we get 6 moles of sodium bromide. All right, so oftentimes students reactant because there's less of it. You're not always given the same exact two numbers. You can't tell based off of how much you're given initially what your limiting reactant will be. You always have to compare in terms of product. And it's always got to be an apples to apples comparison. You can't compare the moles of sodium bromide to the moles of sodium because they're not the same thing. So now that we have an apple to apple conversion, we have them both looking the same, we can see what's our theoretical yield, what's our limiting reactant. So this number is smaller, so this is the important number. I'm going to cross out the larger number. It's gibberish, it's crap. We're never going to make 6 moles of sodium bromide. At the end of the day, given the fact that we have 3 moles of each one of these reactants, we can only make 3 moles of sodium bromide. The max amount you can make is called your theoretical yield. And I'm going to do TY for short in the future. So smaller number is associated with your theoretical yield. You're going to cross out the larger one, so you're not even looking at it, not even thinking about it. Then you go back over here. Your theoretical yield is always associated with your limiting reactant. So I know that sodium, in this particular case, is my limiting reactant. The thing that doesn't run out, that doesn't stop us from maybe making a little bit more, is known as our excess reactant. And I'm going to label those from now on as ER. So the excess reactant is the thing that at the end of the synthesis, we're going to have some left over. It's always associated with the larger number, but again, the larger number just doesn't mean anything. Just cross it out and ignore it. Alrighty, so first things first, same as last week, make sure your equations are balanced. This one is not. I have one of those even odd problems. We got 2 oxygens over here, 3 oxygens over here. So in order to start fixing that, I'm going to throw a 2 out front here. That'll give me 6 oxygens, so I know I can get this up to 6 at some point. Seems like the point is now. I'll put a 3. 3 times 2 is 6. 2 times 2 is 4, and I can throw a 4 in front of my aluminum. The amount of reactants was arbitrary. I just usually have students pick some numbers so that I show you that these kind of problems can work with any quantities of materials. So let's just invent some random numbers. So say you had 2 moles of aluminum and you had 3 moles of oxygen gas available. Again, these numbers reflect how much material you have available, usually, or how much you're willing to mix. 2 lines, always 2 lines, and you always want to analyze the product. You want to compare product to product, apples to apples. So I'm going to ignore this for a second and start with my aluminum. So I have 2 moles of aluminum. I'm trying to get rid of moles of aluminum. So I'll put that in the denominator. I'm interested in moles of aluminum oxide. Mole to mole conversion factors. So I'm going to put the 4 here and the 2 here. So, oh, that's just 1, right? 2 times 2 divided by 4. So 1 mole. Moles of aluminum, cancel with moles of aluminum. So that's going to be 1 mole of aluminum oxide. Now we're going to do the same thing, except we're going to ignore the fact that we have 2 moles of aluminum, and focus on the fact that we have 3 moles of oxygen gas. Trying to get rid of the moles of oxygen gas. And turn it into moles of aluminum oxide. I'll fill out my mole-to-mole conversion factor. So there's a 3 there and a 2 there. So again, I guess with these easier numbers, I can do this in my head. This is just going to be 2 moles. Always check how your units are canceling. So moles of oxygen cancel moles of oxygen. And we're left with moles of aluminum oxide. Alright, so the larger number, I can't emphasize this enough, the larger value of product is meaningless. We're never going to produce 2 moles of aluminum oxide. We just don't have enough aluminum because our smaller number is our theoretical yield. That's how much product we can make. Our theoretical yield is always associated with our limiting reactant. And the number that we crossed out is always associated with our excess reactant. So aluminum is our limiting reactant. That's what they asked us to identify. And oxygen is going to be our excess reactant. Now that we know how to identify the limiting and excess reactant, let's work on problems where we need to calculate how much of the excess reactant is left over. Remember, the limiting reactant is going to run out. We're going to have 0 of that. But we need to also know how much of the excess reactant is left over for purposes of maybe waste, or maybe we need to recover some of that excess reactant and use it again. So there's value in knowing that number. So the beginning of the problem is going to start the same. We're given 2 reagents, the iron 2 sulfide and the hydrochloric acid. We're going to focus on them one by one. Also, the equation is already balanced, so I'm not going to worry about that. I did double check that it's balanced. A couple of things that are a little bit different. We have 2 products. Focus on one product. It's totally up to you which one you pick, and you're going to get the same answer either way. So I'm going to pick iron chloride. Okay, you could pick the H2S as well, the dihydrogen sulfide, totally up to you. Pick one product though. Again, it has to do with that apples to apples analysis. We can't compare iron chloride to dihydrogen sulfide. It's just not a valid comparison. So we're going to change both of these reagents into the iron chloride. I'll start with 0.223 moles of iron sulfide. I want to get rid of the iron sulfide, so I put that in the denominator. And I'm going to change it into moles of iron chloride. Grab those mole-to-mole conversion factors. So there's a 1 out front here and a 1 here. They're both understood. So moles of iron sulfide cancel with moles of iron sulfide, and I get 0.223 moles of iron chloride. I'm going to repeat, ignoring the iron 2 sulfide for a second and focusing on the hydrochloric acid. How much iron chloride can I make from this amount of hydrochloric acid? So start with the number they gave us. We're getting rid of the moles of hydrochloric acid. And we're going to change it into moles of iron chloride. Grab your mole to mole conversion factors. So I have a 2 there, I'll put that there, and a 1 there. Check how your units are canceling. So we're just left with moles of iron chloride. So I'm going to do 0.652 divided by 2, and I get 0.326 moles of iron chloride. Alright, so the same things that we just talked about still apply. We're only going to add on a little extra part at the end to answer the question about how much is left over. So the larger number, gibberish, cross it out. The smaller number is known as your theoretical yield. That's how much iron chloride you could potentially produce given the quantities that you have on hand. The theoretical yield is always associated with your limiting reactant. So iron sulfide, right here, this is my limiting reactant. It runs out completely when I make this quantity of iron chloride. The one with the larger number is your excess reactant. So hydrochloric acid is my excess reactant, which means that after I do this reaction, I'm going to have some hydrochloric acid left over. How much? Well, how you figure that out? You're going to take your theoretical yield. So let me write these steps down. So first, identify the limiting reactant, excess reactant, and theoretical yield. That's what we've been practicing. Second, you're going to use your theoretical yield to calculate how much excess reactant is actually used. So how you do that? Take this theoretical yield value and set up a third dimensional analysis line. So I'm going to take my theoretical yield, the 0.223 moles of iron chloride. I'm trying to make 0.223 moles of iron chloride. How much hydrochloric acid do I actually need? So I'm going to get rid of moles of iron chloride and turn it into moles of hydrochloric acid. Grab those conversion factors. So 1 mole of iron chloride and 2 moles of hydrochloric acid. Look at how stuff's canceling. And so at this point, I'll do 0.223 times 2, and I get 0.446 moles of hydrochloric acid. Starting the dimensional analysis or the stoichiometry with the theoretical yield, this is going to tell us how much hydrochloric acid was actually used. How do we find out how much is left over? Well, we know what we started with. So we had 0.652 moles of hydrochloric acid to start. And then right now we use the theoretical yield to figure out how much we used. So we're going to subtract. So step 3, subtract. And I'll set this step up right here. So you're going to start with the 0.652 moles. When you do subtraction, the units have to match. So there's going to be problems where it might be more natural to have everything in grams, but then you should be subtracting grams of blah, blah, blah minus grams of blah, blah, blah. Apples to apples, we can't mix and match whenever we want. So we're going to do 0.652 moles of hydrochloric acid. This is how much we had at the start, minus the number we just calculated, 0.446 moles of hydrochloric acid, same units. This is how much we used. And that's going to equal, real quick here, we got 0.652 minus 0.446. That's going to equal 0.206 moles of hydrochloric acid. And that's how much is left over. That's the value that they asked us to solve for. So the answer is 0.206 moles of hydrochloric acid left over. Alrighty, another problem super similar to the last one. We're going to take the same steps. First off, it's balanced. I double checked that. And now we need to identify the limiting reactant, the excess reactant, and the theoretical yield. So I need two lines to do that. I'm going to start with the 4.2 moles of zinc sulfide. I need to get rid of the zinc sulfide, so I'll put that in the denominator. And I'm interested in how much product is formed. However, there's two products, so I'm going to just randomly pick one of them. Pick whatever one you want. You'll get the same answers. So I'm going to do zinc oxide in my numerator. And I need to fill out the mole-to-mole conversion factors. So there's a 2 here and a 2 here, which means that I'm going to make 4.2 moles of zinc oxide from the 4.2 moles of zinc sulfide. Let's ignore the zinc sulfide information for a second here. We're going to repeat with 6.8 moles of oxygen. Let's get rid of the oxygen. And we're going to turn that into moles of zinc oxide. Grab our coefficients. So we got a 3 in front of our oxygen and a 2 in front of the zinc oxide. So in my calculator, I'm going to do 6.8 times 2 divided by 3. And I get 4.53 moles of zinc oxide. Alright, so just like in the previous problems, we're going to ignore that larger value. We do know that the larger value is associated with our excess reactant, or excess reagent. So oxygen is in excess. Our smaller value is known as our theoretical yield. Theoretical yield is always associated with our limiting reactant. So zinc sulfide is our limiting reactant. It runs out completely and we're not going to have any left over. Now to figure out how much oxygen gas we have left over, we're going to grab our theoretical yield and convert it back to oxygen gas. So I'm going to start with the theoretical yield value. And I want to get rid of the moles of zinc oxide. And I want to turn it back into moles of, oxygen gas. So coefficients, we got a 2 and a 3. And so in my calculator, I'm going to do 4.2 times 3 divided by 2, and I get 6.3 moles of oxygen. When you use your theoretical yield and turn it back into your excess reactant, that always tells you how much of that excess reactant was used. The problem's asking us how much is left over. So we're going to do the starting amount minus how much was used and that's going to tell us how much is left over. So in this case, we have 0.5 moles of oxygen gas left over. And that's our answer. It took a little bit of work, but that's our answer. Please don't let these different types of problems deter you. You have the skills you need to solve something like this. The only difference between this problem and the previous problem is that we're starting with grams. But you already know, if we're in grams, we need to go to moles so that we can do that mole-to-mole conversion factor. Let's set it up. I did the molar masses over here ahead of time. So the 4 phosphorus and the 2 chlorine. Let's start with the P4, and it's in grams. So I'm going to grab the molar mass, 123.88 grams of P4. Remember, your molar mass always has 1 mole. I don't need to worry about the coefficients of the balanced equation when I use molar mass. At this point, I want to get rid of moles of P4, and there's only one product, the phosphorus trichloride. So I'm going to be turning it into phosphorus trichloride. And let's grab those mole-to-mole conversion factors. So there's a 1, that's this one here, and then there's a 4 here, which I'll put here. So in my calculator, I'm going to do 45.69 times 4 divided by 123.88. I get 1.475. I'm not going to worry too much about sig figs until I get to the end of the problem. So just keep some extra digits and we'll sort it out at the end. So 1.475, you can keep a couple more if you want. 299. What are our units there? So moles of P4 cancel with moles of P4, and then I'm left with moles of phosphorus trichloride. I'm going to set up something similar for the diatomic chlorine, the chlorine gas. So I have 131.3 grams of Cl2. First, I need to get it to moles. So I'm going to put the 70.90 grams on the bottom. And 1 mole, because it's a molar mass, of Cl2 on top. So that gets rid of grams of chlorine. Now I can convert my moles of chlorine to the phosphorus trichloride. So moles of chlorine will go on the bottom so that this cancels this. And then I'm going to do moles of PCl3 on top. There's a 6 here and a 4 here. So in my calculator, I'm going to do 131.3 times 4. Usually at that point, I hit enter. And then since there's 2 different numbers on the bottom, I am going to use parentheses. So 70.90 times 6, close parentheses. Here I'm getting 1.234603 moles of PCl3. So with this information, we have 2 numbers that both have moles of PCl3. So we're able to compare them. Now we have an apples to apples situation. Our theoretical yield is here. So that theoretical yield is associated with the chlorine, which will be our limiting reactant. This is a great example of a situation where if you had just looked at the initial gram values and you said, well, there's less P4, so that's going to be my limiting reactant, you would have been wrong. There's not a way to predict just by looking at those initial values, because molar mass and mole to mole ratios affect what your limiting reactant will be at the end of the day. So here it's going to be the chlorine, and I'm going to cross out the larger number because it's meaningless, and that means P4 is my excess reactant. So let's take that theoretical yield and figure out how much of the P4 did we actually use to make this much PCl3. So 1.234603 moles of PCl3. I want to get rid of moles of PCl3, and I want to turn it into moles of P4, my excess. I'm going to grab my conversion factors. So I have a 4 down here and a 1 up here. At this point, I would have how many moles of P4 I used. However, I can't subtract grams of P4 that I had initially minus moles. The units have to match exactly in order to subtract. They want the mass in grams anyways. So let me take this problem one step further and get these moles of P4. I'm going to use 1 because I'm going to get it into grams using my molar mass. So in my calculator, I'm going to do the mole value times 123.88 divided by 4. And I wind up with 38.2356 grams of P4. And this is how much was used. Again, I'm not too stressed about sig figs because my final answer is just the mass of P4 left over. So at that point, I'll look at the sig figs. So we have 45.69 grams to start. That was my starting amount. And then we just determined that we used 38.2356 grams of P4. Matching units, so it's definitely something I can subtract. So I'm going to do that calculation. And I wind up with 7.4544 grams of P4. However, since remember the rules for sig figs with adding and subtraction? It's all about those decimal places. So since this went to the hundredths place, over here, my answer can only go to this hundredths place. So I'm going to say that I have 7.45 grams of P4 left over.